So welcome to the next part of my lecture. This part now will be mainly on the atmospheric influence, like we have seen before. Also we started with some problems we have in the atmosphere, but now we can see how you can calculate them, what is the scientific background behind this problem in the atmospheric with the atmospheric attenuation we have from the atmospheric effect side. This is this part 2. And in the last part you will see is only the results on the fog measurements. This is the last part, the third is really the shortest one. So this one is a little bit perhaps more need your concentration, but the last part is then more easy at the end to understand. I think most of you know that this idea from optical wireless is not so young, as you can see here, more than 130 years ago, the same Graham Bell, who invented the telephone, also had an idea on a photophone. He called it photophone, and it was really working. He used as a transmission light, he used the sunlight. He had a mirror there, and with this mirror he directed the sunlight to a membrane of a mouthpiece, where have been the speaking modulated, with this membrane to the sunlight. Sunlight was the carrier frequency, and the speaking was the information, the lower frequency, the modulation frequency, and this was transmitted, it is written there, around 200 meters. You can see nearly the same distance, like we had in some of our self-developed systems. And on the other side there was some earpiece, and this person on the other side could understand the information what was given by Graham Bell with the mouthpiece. So that is a very old technology in principle. And in principle the optical communication, it is in history, you cannot say where the optical communication is starting. Was it also some science with smoke or flags? Is also in principle optical communication, but the data rate was very low, of course. But he has done really the same like we are doing, real communication. He started, Graham Bell, the same scientist who had invented the telephone, in 1880. Is only for interest to see. This figure we know, Let's come to the principles and to the influences. As mentioned, the three main influences: the molecular absorption, the scattering on the particles, and the atmospheric turbulences. Let's start with the molecular absorption. We know in the atmosphere we have different types of molecules available, and of course these molecules giving us some attenuation. As mentioned before, the attenuation we can split in attenuation by absorption, that is the first part, and the attenuation by scattering. And the smallest particles are the molecules. And the same equation, of course, we have seen before also. You have an intensity available at the beginning of the medium, and the path through the medium, at the end you have some lower intensity in principle. Otherwise you would have some amplifier in between, but usually you have some attenuation, so the intensity E would be lower at the end of the medium. And of course it is dependent on the attenuation or absorption exponent, alpha, and on the length, the thickness of this medium. And also if you combine this exponent alpha multiplied by the length. You can say that it is the optical thickness of this medium. It is always the same equation we know, also on different names. Yes. Before I think we have seen it as Beer-Lambert equation. Yes, but you can also find it on some other names, but it's always the same principle we have. And you know, all these medium in between, these molecules, we have different molecules, and different molecules have different absorption lines. Yes? And so you have in principle not only one type of molecule, not only one gas, you have usually a mixture of different gases. Yes? With different of these absorption lines. Yes? And these absorption lines make this, bring into this attenuation of this molecular absorption. But it is predictable because we will see it is always the same. Yes? And of course you have one part, this is the absorption part and the transmission part. And of course, as mentioned, in principle it is inhomogeneous because that would be a very easy case if you have homogeneous, all the same molecules, all the same particles. Usually it is inhomogeneous. Yes? And instead of this equation before, you would have an equation with an integral. Yes? To consider a length of a medium, a layer. Yes? And within this layer you have to take the integral of this. And of course you have this, instead of this parameter with the absorption and the length before, we have now to consider a concentration, a density of the absorbing particles, this n of z, yes. And of course you have the location, the z coordinate included, and of course the, like we have also in the radar, the absorption cross-section. That are the equations, the scientific equations, the scientific science behind, yes. And you have of course the absorption part and the other part which is passing the transmission part. Yes, one part is absorbed and the other is transmitting. Yes, is transmitting. Yes, and of course, if you have also big part of scattering, you have also, we will see later, to consider the scattering part. Yes, absorption part plus scattering part. Yes, is the lost part. Yes, the transmitting part. Yes, is the rest of this part which has been considered under absorption as attenuation and scattering as attenuation. And also if you have the scattering, not all of the scattering part is always lost, because you have multi-scattering and some parts of multi-scattering perhaps you can use on your receiver system. Yes? So this has also to be considered for further ideas on this optical wireless system, on this optical wireless communication. But here we have this non-homogeneous or inhomogeneous absorbing medium. And of course, it is also a difference if you are near the Earth or on higher region, near the troposphere or around end of the troposphere. Yes, because the concentration and the type of the molecules are different. Yes, and if you see the equations here, then you can see there's mentioned Lorentz distribution somewhere, or Lorentz equation, or Lorentz spectrum, and it is similar to understand like you have a gas laser. You know, a gas laser, most of them are working in homogeneous or inhomogeneous line distribution. Their working point, and you have also there a Lorentz distribution and the Doppler or Gauss distribution. And it is similar here, yes, because near the Earth the molecules are not so rare than in higher regions, yes. So the mixture of the gases, they have the molecules have a velocity all the molecules, which is in middle the same. The middle of all the molecules movement, yes, is the same, yes. And of course, this movement molecules, this movement, this velocity is going into the equation, yes, but all of them are the same, so you have no Doppler shift or no Doppler frequency, whereas you, in the higher region, end of the troposphere, or in this region, yes, or above a little bit, you have more rare and rare molecules, yes, and they have, of course, because they are more rare, they can move more independent from each other, yes, and so, of course, their own movement, yes, will make higher influence on this distribution, yes, and also on the absorption lines at the end, yes, and so this is called then the Doppler distribution or the Doppler effect on the higher regions. Yes, that is the main difference. I always try to make it understandable to optic people when they know from the gas laser. Yes, because we know in the gas laser you have homogeneous or inhomogeneous working case in most of the gas lasers, and in inhomogeneous you have also this Doppler frequency or Doppler velocity or Doppler shift, yes, and the same is here, yes, because in gas laser you can very easily see it. Gas laser with high pressure under high compression is homogeneous, yes, Lorentz, and under low pressure it's banding gases, yes, in gas laser also you have this Doppler shift, yes, and it's the same situation here, and so that is the reason why you get these equations here for Lorentz equation near the Earth, yes, and in higher region we can see then after that, of course, you have to calculate it with the pressure and with the temperature, because we know if you go up in the from the Earth ground, yes, to the troposphere, then usually, yes, usually the pressure and the temperature is decreasing. Yes, this is also influencing the refractive index. We will see later in the atmospheric turbulences. Usually, yes, only in inversion cases it can differ. Yes, but usually it is decreasing with the height. Yes, pressure and temperature is decreasing. Yes, and that means also that the refractive index usually is decreasing. Yes, with the height. Yes, and that is also visible, of course, in the equations and with the distributions. Yes, so we have this Lorentz distribution on the level of the near the Earth, and later this Doppler broadening or Doppler distribution on the higher halves of the atmosphere. Yes, you see it here in this difference. And as you know, in gas laser it is similar. Yes, with under high pressure and low pressure, with homogeneous and inhomogeneous. So I think that is easy understandable from this side. Also, if you are not a physics guy, yes, if you are an electrotechnic guy, familiar with optics, it is easier to understand, yes, to have this considered like in gas lasers. So you can see this distribution here, again summarized with this Doppler broadening, but that is the scientific background equation, yes. But what are the results for us? Yes, because that looks, if you see this equation, you see which parameters inside, but we cannot have some value. Is it high attenuation? Is this distribution, what does that mean? Yes. So for us it is better visible in the next figures, or in the, here it is summarized which types of gases and molecules are available, yes, and here you can see in this figure the absorption, 100% or 0%, and one graph is on the Earth, and the other graph is on the edge of the troposphere. The upper one is on the Earth, and the lower one on the edge of the troposphere. From the from the point of view, it would have been better to have both graphs in a different way, because then it is easier, because the lower is on the Earth, but in this way the lower is on the edge of the troposphere, yes, on the edge of the troposphere, and this one is reaching the Earth, is near the Earth, yes. And you can see, of course, they are different, because of the different molecules, the different types of distribution, Lorentz distribution or Doppler, Gauss distribution. You can see that there are different windows which are not so much absorbed like others. Yes, and as you can see here, at around, in principle, at around in the visible light area, 0.5 up to around 0.9 or up to 1 micrometer, the absorption is low. Yes, so you can, what is also understandable, because otherwise the sunlight would also not come, or the real visible light would not come to Earth if it is not, if it is absorbed 100%. Yes, so this absorption this absorption effects by the available molecules there in the troposphere, they are low in these areas. Yes, so we have a very good transmission in this region, where usually the oldest technology in optical fiber and optics work, the first window, as we know, in the optical fiber at around 0.8 micrometer, yes, the first optical window in the fiber, yes, is also well suited for optical wireless in the free atmosphere, like we have here visible from the point of this molecular absorption. Yes, and also if you see there at around between 1 and 2 micrometer, it looks also good. And here we have also windows which around the points of 1.3 and 1.5 micrometer. So all the used technologies or all the used wavelengths in fibers, yes, are well suitable also in the atmosphere, yes, from the point of this molecular absorption. Yes, and these are always nearly the same. Yes, they are predictable. Yes, they are always of the same value. Yes, that was, and here we can see what are the influence of them. Yes, so this molecular absorption is not a big issue for optical wireless. Yes, because it's the same and is forecastable and predictable all the time. And perhaps one back, you can see here which types of molecules are available in the atmosphere, in these regions of the atmosphere, and which spectrums or which spectra they influence. Yes, so that is summarized here on these slides here. We know the typical water vapor, of course, carbon dioxide, yes, ozone, nitrogen oxide, methane, oxygen. Yes, that's the typical. And of course, these absorption lines, they have very often some higher frequencies also on other wavelengths. Yes, some sub-harmonic and so on. Yes, but that is the usual what we have for this molecular absorption in detail. So they do not really high influence our optical wireless system, because we know how they work and we know what are their attenuation and what are their windows. Yes, so it is important that we can use the same windows like we have in fiber. Yes, because that is also reducing the costs of the systems. If we have to invent new systems with other wavelengths, it would be more expensive or additional expensive compared to these usable technologies. So that was the absorption, the molecular. Yes. The next point would be the scattering on particles. Yes. And of course, scattering on particles, we have the smallest one, again the molecules, or larger one. And the smallest one are again these small particles are again the molecules. They are the smallest. Yes? And of course, this smallest particle, this scattering is Rayleigh scattering. And if you have only this Rayleigh scattering, you can see then the visibility is 350 kilometers. Yes? And it is a good value. Yes? If you can reach 350 kilometers, yes? If there is no fog, no clouds available, then it is a good visibility. Yes? Of course, if you come to higher regions, then this is becoming better. Because if you are going outside of the troposphere, yes, the molecules will disappear. Yes? They are only really like vacuum further from the Earth away. Yes? Then of course you have also not this limiting factor of molecular absorption and molecular scattering. Yes? So it's much more better. Yes? So now it is understandable that optical intersatellite links are very well working. Yes? Because they are at minimum, if they are geostationary satellites, they are around 36,000 kilometers from the Earth. Yes? There are no value influence and also very low chance for molecules. Yes? So that is very good for these optic intersatellite links to have high quality communication link. So that is really easy to understand. Yes? So these molecules are producing this Rayleigh scattering, which is proportional the frequency to the power of 4, yes, as we know, for very small particles. Yes? And all the other particles, starting from some aerosols to fog, up to rain, yes, or in between clouds, yes, they are more problematic because they are with the me or my scattering, yes, and the most enemy, of course, the fog and the clouds, because in this case the my scattering is most important, yes, for the particles which have the same size like the wavelength. Yes, so all of the larger particles are for my scattering, but clouds and fog are the most relevant, of course. And in the next point, we see summarize this Rayleigh scattering. Here we have this equation for that, for the Rayleigh scattering, and as mentioned, it's mainly these gas molecules. Yes, these gas molecules, they are producing this Rayleigh scattering with the equation there, the scientific background on it. There's also, of course, you can see the refraction index in the equation. Then, of course, the number of gas molecules, the important factors, the wavelength, of course, and there's also some depolarization coefficient of the medium by the scattered light radiation. Yes, that is very interesting. We will see later. Most of these measurements and all of these empiric equations have been generated mainly by people who are mainly working on exploring the weather. Yes, with LiDAR and radar, in this case more with the LiDAR. They have generated mainly these equations, but have not known, of course, at this time that it could be relevant for optical communication also. Yes, and most of these equations are empirical. Yes, they have measured a lot of cases of different weather situations for a long time, and they tried to generate from these measurements an equation. And all these equations are called empirical equations. Yes, it is easy to understand if you have an Excel sheet, and in the Excel you have your measurement data. And as we know, also in the Excel we can say, please make a curve fitting to most of the points, of the measurement points, by this polynomial or something else. Yes, and also this with this curve you can, in principle, make such an empirical equation. Yes, because in former times, when they made these empirical equations, they had not a computer and not a calculator sometimes. Yes, we will see later one scientist who has calculated in 1950 somewhere a lot of tables, yes, with such measurements by hand, yes, because at this time also not a calculator was really available, yes. So sometimes it is amazing how people in former times worked, yes, and now we have so much things, and we have, but of course, also the time was slower at this time. Yes, sometimes it had also an advantage. It was slower. It was not so stressy than we have nowadays. Yes, but that is always a point that you should remind that in former times they have also done good work. Yes, by hand. Yes, not only the mathematicians from the 70s or so, also other scientists. Yes. And as mentioned, this is the Rayleigh scattering, the equation of these gas molecules. And now, this is also, of course, summarized in different, because I mentioned they have made measurements, and from the measurements they derived the equations. And of course, they have also summarized as in tables, yes, because in former times it was easy to have a table instead of some curves, yes, because if you have a curve, you make a copy, then it is not good visible, yes, but the numbers are still always readable in principle, also if you have a copy, yes, so they have it very often on such tables, and of course for different wavelengths and heights, yes. In this table, the wavelength you can see is the parameter which is changing, yes, on the first column, yes, is the wavelength changing, and on the next is the similar but not changing the wavelength, only for 3 different wavelengths, changing the height, yes. You can see the Z, the kilometer, the height is changing for 3 different values of the wavelength, yes. So this is summarized in these tables, which are very often much more, in former times that was more comfortable because of mainly copy. Yes, you can copy easier or write it easier than to make, because in former times when they are not able to make a copy, they could write it. That was easier to write, yes, than to make the curve drawing. Yes. That is the point. And as mentioned, mainly the specialists, on the scientists on weather, LIDAR and so on, they have made these experiments. Okay, scattering on particles. In principle, of course, we have, as you can see here, the part of the scattering, and of course we have the part of the absorption, like we have heard. That is, of course, also not only on the molecules, that is also the larger particles. Yes? But on the larger particles, of course, the part by scattering is usually the bigger one. Yes? The most relevant, because of this Mie scattering, because this Mie scattering is a really big factor, a big attenuation factor for our optical wireless systems. Yes? But in principle, of course, we have also the scattering and the absorption part, and together it is the whole extinction or the whole attenuation part. Yes, and also you can see here again, usually the medium is not homogeneous. Yes, so you have to take the integral, yes, of a part of some part of the medium. Yes, that is the why you have to integrate to take the integral. And the point is, also for integral, to take the integral is that the concentration is not always the same. Not only there is a distribution, yes, and that is usually much easier to solve with some integral like we have there. Yes, you have, as example, very often you use that you have a medium value of the size of the particle, yes, and the distribution of that, and then you can calculated or recalculate from one side to the other what you need for your analysis for this scattering effects on particles. But they are the general equation we see here. And of course the size is the important parameter. And if you have the distribution, then of course the medium value of the size is important, because the distribution you know, and with the distribution you can calculate that. There was, we see again the same equation here. Yes, now it is not as Speer-Lambert, it is as Puget law. So you see in literature different laws for the same. Yes, because a lot of people contributed to that. Yes, and of course also again inhomogeneous is the most, or non-homogeneous medium is the most interesting. Like you can see here with the integral. Yes, from a special length, yes, of the medium, from 0 to the length n. Yes, and again the attenuation and the z coordinate, the intensity at the beginning and the intensity at the end. And the wavelength, of course, is also a parameter there, as we can see. And as mentioned, this scattering of particles here, yes, there's a scattering part and the absorption part, but the me scattering is so big, yes, that the absorption part is really not important. Yes, it is the scattering part which is the important part. And usually we have non-homogeneous medium. Usually, if you have the good luck to have homogeneous, then it's really good luck, because usually it's non-homogeneous. And as you can see here, me was one of the first people who has done all these scattering experiments now more than 100 years ago. And he has not only done it for the optic, he has done it also in the whole area from the, he's also very important in the RF field. If you have radar technique, then you also will hear about me, yes? But in the radar technique, of course, the particle size and the particles are more the rain are the interesting particles, yes? That is also the point why a weather radar is very well, can very well estimate or very well predict rain cells, yes? So that is the reason why radar, yes, me scattering, microwave is well connected, the most attenuation for the rain particles, yes, the particle size, yes. And in our case, of course, it is the smaller particles like we have in fog and in clouds, yes. But that is in principle the equations we have for me, yes, where you have again this cross section there, this sigma, yes, the size of the parameters, of the particles, this A, yes. In principle, there's also a normalized size, you can see later, this X, yes, where this A is 2 times with B multiplied by the wavelength lambda divided. And also, you can see for the refractive index, they have also taken care on not only on a real part of the refractive index, they also considered the imaginary part or the whole complex part. Yes, in radar technology that is also very important. And one very important person for our aspects in the optic was Van der Hulst. Yes, and this was this guy I mentioned before. He was calculating everything by hand with a lot of tables. Yes, done that in 1957, as we can see. Yes, and he has really calculated with this complex refractive index with imaginary and real part, as you can see there. Yes, the air, of course, he took with 1. Yes, it is this M2 with 1 the air, but the particle was considered as this imaginary or this complex refractive index. Yes, and there exists a lot of tables in his book. Yes, we had this book at our institute. I used it also for my PhD thesis, and at this time when I used it, it was before, when I got it, it was really a destroyed version, yes. And later, I think 10 years ago, now 10 years ago, I ordered some book by Amazon. It was also something with flight scattering. And then there was an option, would you also like to have the book from Van der Hulst, really from 1957, for I think €5 more or something. And I said yes, and now I'm really happy that I have a new version or a newer version of this Van der Hulst. It's a really a good book, because if you really consider it under the aspect that he had no calculator and no computer, yes? And he had really so much different examples and calculations. Yes, he said there is not only this water drop, there is a neighbored water drop. And then on the next side, there's not only one neighbored water, he also considered multi-scattering. Yes, that was really very, very interesting. Yes, and he was very famous of this. So all these equations now are mainly from his book, yes, originally, because he has done this work, of course. But for us, of course, it is mainly of interest clouds and fog, because it is the main attenuator. This is doing the, perhaps as example, if I told you before that dense fog in Graz will cause around 30 dB per kilo, 300 dB per kilometer. Now, 30 dB per kilometer in Graz, yes. In this 300 dB, a typical dense fog. And if you compare it with the attenuation caused by rain, then it is 2 or 3 dB per kilometer at maximum usually. Yes. So the value is much lower on rain. That means it means, of course, attenuation exists also for rain. Yes, but the rain attenuation is much lower. Yes. So the fog and the clouds, because the particle size is at the same value, is most effective for our optical liners. Yes. And you can see here on these equations, you have, of course, the number of particles here inside, the concentration of particles, this NP. Then, of course, you have can consider the number of particles, but also the content of water vapor, this QW, yes. And in all these equations, in both, you can see, of course, the visibility, yes. And in one, you can also see the density of the water vapor, the water density, this rho m, yes. You see this rho m in water density. This is going into the equation for this water vapor concentration, yes. But in both equations is this visibility, this Vm inside, and you can see this visibility is a very important value, a very important parameter to predict fog or cloud attenuation. Yes, because you see also this parameter again the size of the particle and some other mathematical aspects, like we have here the gamma function and this factor f of 0.5, but 0.5 is wavelength they used, yes, but this is the most relevant factor is the visibility, yes, the not mathematical, yes, that is visibility is really found by empirical, by experiments, yes, because also these equations here derived from calculations of scientists and from experiments, of course. And one of the greatest of these calculators, of these scientists, was Van der Hulst in this area, yes. And there's also an interesting aspect which I should mention perhaps here. If you have the visibility, then of course you could very well predict the attenuation, yes, but it is not 100% possible to do it in the other way. If you have the visibility or the attenuation, yes, you cannot 100% say which type of cloud or fog is inside. Yes? Because if you have only the visibility value or only the attenuation value, then it could also perhaps be a different size of the particles and different density, causing the same visibility or causing the same attenuation. Yes? So the way back is not possible usually. Yes? So if you have the visibility, you can say, okay, this is the attenuation. Yes? Also, you can calculate it directly from the distribution and the drop sizes, yes, the attenuation of the visibility, but not in the other way, yes, because I hope you understand my complicated try to make it understandable. If you have only the visibility value, yes, then I think 4 or 5 possible scenarios would be possible which type of fog or clouds you have measured, yes. I hope that was understood. We will see it, I think, later for some other slide. That is also the point what is making something more complicated. As example here, you have here an attenuation factor. There's the visibility, you see, yes? All the time for all the measured in the table, measured scenarios or calculated scenarios, you have always the same visibility, yes? But not for all of the same visibility, you have not the same particle size or not the same density of the clouds or the tops or the particles. Yes, you can see here we have always the same visibility, but these parts can differ. Yes, so the way back is not possible. Yes, but you can calculate from the visibility relatively well the attenuation. Yes, because for the attenuation, if you have the visibility, it is not important have there been only a few particles with a bigger size or have there been a lot of particles with smaller size. That is for the attenuation not important, and for the visibility because it could be the same. Yes? So the way back in this way is not easy or not. It is possible, but you need an additional parameter if you want to make it recalculated. Yes? That has also been done by some of my PhD students. We can see in the last presentation. Also there is of interest because perhaps you have heard a lot of people propagated you should use instead of 0.8 micrometer or 1500 nanometer, you should use 10 micrometer because that is much more better in the case of fog and cloud attenuation. What is true in principle, because if you, for the 10 micrometer, you need larger particles in the fog or in the clouds, yes, and so you are more in the domain of RF or of the rain, yes, so 10 micrometer particles are much larger than the particles in fog and clouds, usually, yes, and so you can also see here, if you have these particles available in the atmosphere, then you can see the smaller particles here have higher attenuations on the lower wavelengths, and of course for the higher wavelengths it is much better, yes, but also for the 10 micrometer particles it looks that the curve shows that in principle the attenuation is better. Lower attenuation. Yes. So this figure shows that to use 10 micrometer could be better. Yes. But otherwise, it is clear. Otherwise, nobody has checked what is with the attenuation by rain. Yes. So if the attenuation by rain becomes much more worse, yes, so then the benefit is not so high. Yes. Because you shift from one problem to another domain. Yes, but in principle for fog and clouds, 10 micrometer would be fine. Yes, but also we know for 10 micrometer it would not be easy to find transmitter and receiver. Yes, very high price and not so good working components, and very high price of course for that, because nobody will need it, because in fiber you will not need 10 micrometer. In fiber you can use 1500. But of course, you will see later also, there is of course an advantage to use 1500 nanometer instead of 800 nanometer. Not at the intonation, there's not much different, but for the laser and eye safety, yes, because for 1500 nanometer, you are more far away from the visible light, and so the light coming to the eye is not focused on the retina directly, yes. So that is not so dangerous for the eye if you have higher wavelength than 1400 nanometer. So 1500 nanometer you can use higher laser power. So that is the advantage why using 1500 nanometer instead of visible or 1300. Yes, but that is the only advantage. For the fog, it is nearly not big advantage. A little bit, but makes no sense. But for the laser and eye safety reason that you can use much higher power, it makes sense. Of course, we also checked, or scientists also checked for rain, and as mentioned, rain attenuation is much lower for our optical wireless. But of course, there exist also similar equations, like we have with here an example with rain rate. Yes, you can use the rain rate there. That is a very estimated equation. The last one, this is the exact one. But the rain attenuation is not so critical, because the Mie scattering is much worse when the particle size is exactly the wavelength size, yes, or the wavelength number. So that is the point why scattering by rain is not so important. Also, different scientists calculated on this. You see again the same equation, so I think originally it has also something to do with Van der Hallstein. There exists also these equations we know for the scattering parameter, for the scattering attenuation parameter, where we have the visibility, a very easy calculation method. The wavelength, here the wavelength is, because it is usual, usually everything is connected to the visible light, to the 550 nanometer, yes. So that is the reason why we have this parameter, the number 0.55, yes. And if the wavelength lambda is the same, then of course it is the best, and otherwise it will be changed a little bit in its equation with this parameter where the visibility is again in the exponent with the number 0.195. This is also an empirical equation. So as you can see, if you have the visibility, yes, you can well calculate the attenuation, yes. But if you have the visibility, you cannot say which type of particles and density exactly was there, if you have not an additional parameter, yes. As mentioned, we tried also to have with an additional parameter to recalculate which type of fog or clouds has been available. Yes, if we have the visibility and some other parameter, we can. Yes, but not directly only with the visibility. That would be too less parameter. And this equation is also well visible in this figure, only done by, I think, some Excel calculation with some numbers. And you can see there's not much difference between the 0.8 and the 1500. Yes, there's not much difference. Also, if you see for low visibility, that means dense fog. Yes, if you have dense fog, visibility only 1 kilometer, then it's nearly the same. Yes, the attenuation, because all curves meet nearly the same point for low visibility. That means high dense fog events. And that is also visible here with 10 micrometer, in other colors. Here we have, of course, more difference. Yes, you have there more difference, and here. But that is only the same equation as we have seen before in these measurements. It looks that in principle, for this 10 micrometer, we should not use, I think, this same equation, because this equation would be too far away with the visible light from the 10 micrometer. Yes? But also with the rough estimation, with the same equation, we can see that, of course, that would be much better for 10 micrometer. But, of course, perhaps other influences. And, of course, we have seen in literature, some people really said it's much better for fog, but then other people said, but for other influences like rain, or also atmospheric, for molecular absorption, it is more porous. In literature you can find different of these statements. Okay, that was the part of the atmospheric influence by the scattering part, and now we have still the atmospheric turbulences. For this part of the lecture. The atmospheric turbulences, as I have mentioned, it is the change of the refractive index, because the refractive index is principally a function of temperature, pressure, and humidity. And usually, as mentioned, if you go up a hill, up to the height in the troposphere, it is slight decreasing, because all these parameters, temperature and pressure, are decreasing, usually, if you have not an inversion case. Yes? And that is the reason why you have different refractive index. Yes? And this different refractive index, as mentioned, it is only changing, it is nearly 1, yes? But in the 6th or 7th position after the comma, there is some change. Yes? And this slight change, it is also, of course, important in RF communication in the troposphere, but also here for optical wireless, because of these changes of this refractive index. If it would be stable all the time, if there is no mixing or changing, then it would not influence. Yes? Because if it is only in the last position, it would not make a lot of influence on our optical wireless field. But the change is making the influence. Yes? And these changes, usually very slow, as it is from 10 Hertz to maximum 1 kilohertz or so. Yes? It is a slow changing, but still too quick for auto-tracking system. Yes? Because the auto-tracking system does not know in which direction the beam is directed. Yes? The beam, when the beam is wandering. Yes? And usually, of course, this is also, we have again a mixture of air, yes, and this mixture is always changing, yes, and of course you can also see it like in a gas, with the gas, in the case with the gas equations, like we have, but that is not so important, and it is not so that we go in detail, but the colleagues from German Aerospace, for them it is really, this part, this atmospheric turbulence, is most important. Yes? But it is only important, it makes only main influence for longer distances. If you have 1 kilometer, you can measure it, yes, but it will not be high influence. And the longer the path, much higher influences you have. And if you have, as mentioned, if you have only intensity modulation, then you have only to see beam wander sometimes, or beam spreading. It depends on the size of these turbulent cells. Yes, it is also a parameter, the size of the turbulent cells, you will see. And only for coherent transmission, it is important because there the phase front is changing. Yes, and if you have coherent transmission, then it is a problem, these atmospheric turbulences. And as mentioned, for intensity modulation, you can overcome it very easy if you have more than one beams in parallel. If you have multi-beam system, then it is not important. Or a little bit larger divergence angle, then it is not important. And only for larger distances. But of course, people exactly try to calculate and to analyze these effects. Like the colleagues in Oberpfaffenhofen near Munich. And as mentioned, only this beam wander and beam spreading is important for our systems. And the distortion of wave and phase front only for the coherent transmission. These responsible turbulent cells we are checking now. It is like in hydrodynamics. If you have in hydrodynamics some cells of water, yes, it is similar. You know these water turbulences are dissipating into smaller cells and so on. The same is also for these atmospheric turbulences. If you have, instead of these water cells, if you have air cells, yes, and you have bigger cells, yes, and they will dissipate with time in smaller cells, yes, and they are making the influence, yes, because of these different cell sizes. You can see here a nice picture of that. Looks here. It's the medium in between. Yes, you have larger and smaller cell sizes, and of course that means beam wander and distortion of the phase front. The colleagues from German Aerospace, they had in this Subnex project, they have made some measurements and later some simulations of this change of the phase front by these turbulent cells. And these turbulent cells, they are mainly defined by some structure parameter or structure function. In literature you can find that with Dn or with Cn, and of course you have always to consider the length of these cells. Yes, you have an R1 and R2, yes, the begin and the end of such a cell, and of course you call it this scale length with L0 here. Yes, if larger cells dissipating into smaller one, then you should have the smaller one in a bigger area. Then you have a outer scale, it's called outer scale, the length of the, let me say, turbulence, of the number of turbulent cells which are of the same type, yes, in some area that is combined as a larger scale and the small scale, the inner scale of each turbulent cell. Yes? So you can calculate that with this structural function or structure parameter. Yes, perhaps you have seen that. Yes, we have never worked with this because we have only measured them 2 times. Yes, but German aerospace colleagues, they work really with these parameters, with this structure function and structure parameter. And of course, not only these 2 parameters, this large scale length, this L with capital L written, and the inner with small letter. Is it somewhere here? Or is it on the next slide? There should also be a small. I think it is on the next slide. There's only the bigger one, the large capital L. Yes, but there exists also, if you have a lot of small turbulent cells, you can combine them again as an amount of big a lot of small cells to a big cell. Yes, so you have this large scale and the small scale. I think that is visible in the next slide. Yes, you have here the small and the large. Yes, the inner and the outer scale is mentioned in the literature. And of course, this parameter, if you have this dn or cn, you can find in literature. If you have the dn, you can make them calculated by a cn. Yes, and of course, there is a difference. What is the relation between the bigger and the larger scales, as example, and of course of the radius r. Yes, that is the point you have to consider, and of course the intensity of the turbulence. If you have weak turbulences, medium turbulences, and strong turbulences. And perhaps there's also an interesting aspect, as mentioned, for us, yes, if we work with intensity modulation, it is only important if there is a beam wander or beam spreading. But this beam wander, if you have intensity modulation, and if you have, of course, multi-beam system or a system with larger beam divergence, if you have this beam wander, that means it is like an attenuation. Yes, because if the beam is not directly going into the receiver as usual, if it is going only a part into the receiver, then you have less intensity on the receiver. Then for the receiver it looks like an attenuation. Yes? So if you like, you can also calculate from this intensity fluctuation we have, you can also calculate some type of attenuation, but only for your receiver system. Yes? Because not the whole beam is concentrated into your receiver, because it is wandering. It is not directly, only part is in the target, so it is like an attenuation. Yes, like or a loss. Okay, you can say attenuation or loss. Like you have a path loss or something, you can also consider that as a loss for intensity modulation. And of course, these turbulences, they are also they are available a lot of different distributions in the literature. Perhaps you have heard of some of them. And of course, also the surface of the Earth is important, because that is understandable. If you have a different surface and the air is changing, is moving, then of course the cells will have different characteristics. If you have perhaps somewhere a wood, or if you have only some meadow, yes, or some asphalt or street or something. Because then of course the air masses are more or less resistance. Yes, the air must have more or less resistance, and so of course the type of turbulent cells are different. Yes, and the type of the turbulences. Yes. Also on water, because the water surface is very flat. So that is in literature. You can find difference for different surface types, yes, different roughness values, and for different distributions, you see these roughness values have an influence. Yes, there's some of this distribution available here. I think this is from the Springer book. Yes, Springer book. Yes, the copy, and of course this is important also for this length generating the turbulent cell. And again, here's some type of distribution. You see here this one model is called the Skurwich model, and I think one is a Hufnagel model and so on. Perhaps you have heard from that. There exist different models. But you see the Cn, this parameter, but the Cn squared is again visible here. And as mentioned, most important is for long distances, and if you have fog or clouds in between, then you have not to consider these turbulences. Perhaps at the end of this turbulence is some summary of special effects you can have. If you consider, it's very easy to understand, if you have a beam, yes, with a diameter which is smaller than a turbulent cell, then of course it is like a type of reflection that leads to the beam wonder, usually. Yes? If you have turbulent cells in the same size like the beam size or the spot size, then of course it is like a lens. Yes? Because if you have a lens, also the beam size is similar to the lens. Yes? So it is the same influence like you have in a lens. Yes? You can also have perhaps a little bit opening, like a small beam spreading, or also some type of beam wander. It depends how the lens is located in your system. Yes? And of course, if the turbulent cells are much smaller, yes, then you have like a scattering effect, that is the beam spreading effect. Yes? Like you have a scattering on small particles, similar, yes, for this atmospheric turbulence. So the beam diameter and the turbulence diameter, turbulent cell diameter is important as well. Okay, before finishing this part, perhaps general, we know we have not only the weather influences, not only the atmospheric turbulences, not only the molecules, of course we have also the usual geometrical losses. If we have a receiver and a transmitter, of course, the receiving part and the transmitting part, the transmitting and receiving part, and the opening angle, of course, yes, then you have also this, you can find it in literature as geometrical path loss, usual, yes, somewhere. Then, of course, you have it is, the losses are higher if the angle alpha is larger, yes. And if the radius, the distance is larger, yes, and if the receiving area is larger, would be better, yes, because it is, if it is better, you can receive more of the intensity, yes. It's easy to understand, yes, but that should be mentioned also on the end, that also the geometrical consideration is important. It is the geometrical, defined as the geometrical attenuation or geometrical loss, like we have in the optical wireless area and optical wireless field. Also in SATNEX, you can see the colleagues from German Aerospace also mentioned, also for the phase front distortion, it is better to use two beams in parallel. I'm not sure if that is true, but they told it in our book in SATNEX. We know for us, if there's beam wander or beam spreading, two beams in parallel or 3 or 4 in one housing would be much better. They also told that two parallel beams would be better. They told on the wave front is better because there is a middle then, but I'm not sure that it is only the intensity what would be better, and so they have the feeling that also the phase front is better. But I have not analyzed that. They mentioned in the book, yes. But in principle it is better for the intensity, yes, to have this multi-beam system in one housing. There is also an additional empirical equation similar to the former one, where you can have absorption and scattering in one combined, but at the end the scattering is the most, so the value will not differ so much between the value between the equation we had before, but in this equation it is mentioned in literature that also the absorption part is included, yes, for this equation. But again, of course, the visibility is here in the equation like usual. So visibility is really an important parameter. At the end, some investigations which has been done for a long time ago at Lucent Technologies. You see here 1999. They have really used a 2.5 gigabit optical wireless system. The distance was 1.2 kilometer. In literature it was also to find that they have done it with money from NASA, yes, as I know. But they had a really good system. They used not only lens system, they used mirror system, and they had here, as you can see, the incoming light. And for the incoming light, they had at first one primary mirror, and from the primary mirror, they focused or they guided the light to the secondary mirror, and the secondary mirror directly focused into the fiber. Yes, so they connected directly into the fiber with this double mirror system. It is perhaps in satellite communication with two mirrors. It is like a Casper satellite antenna. Similar, they used for their system at the Lucent technology. And as visible here, they used three transmitting systems in parallel, three transmit units in one housing, and the fourth one was only for alignment of the laser. That is the laser beacon. I have not exactly checked, but usually they use another wavelength for that. I have not checked which one. Only to make this connection, the auto tracking, this alignment between the two systems. So one was only for alignment, this with laser beacon, and the other three have been for transmitting. And they also used not only such a system for transmission with 1550 nanometer, they also made experiment with wavelength division multiplex. You see here they used 4 channels. We will see later. With these 4 channels, they also used these spatial modulators and optical amplifiers. You see there this lithium niobate oxide, yes, and the optical, they used that as a modulator and the optical amplifier, and then to the telescope, and they transmitted really 4 different wavelengths. We can see here 4 neighbored wavelengths, of course, to demonstrate wavelength division multiplex. As you see here, the 4 carrier frequencies for the 4 different channels they used over the free space there. So that was a very well working experiment with 2.5 gigabit per second, and they used an analog photodiode for receiving element. Of course, that is a typical good possibility to use with WDM, with this wavelength division multiplex system, to connect 2 different networks or 2 different routers somewhere, yes. Because in principle, optical wireless, we know, is only an extension to the fiber or a supplement to the fiber, yes. The same what we can do with the fiber, we should also be possible with the optical wireless system. And we can also, because we know the wavelength division multiplex, if we have the carriers, yes, then we, related to RF, we have still a big bandwidth available, yes. So we can also try to mix it with some kind of RF technology, and you can also have on each of these carriers of the wavelength division multiplex, yes, you can also use some microwave subcarriers to have additional channels available, because sometimes you have the microwave channels, yes, and you can use it as these microwave subcarriers, and then you have these all these different. You can have additional 10 or something subcarriers, microwave subcarriers on each of the wavelengths. And that is again our system. As mentioned, we mainly used it for the last mile access. We had also some tries, as visible here, to use some in between of the campus, some type of multi-point central station, and to combine 4 or 5 systems together. Yes, but of course you have to use for this central station 4 or 5 different point-to-point systems to connect the different locations. But that was our central station at this time, at our campus in Graz at this time. But of course we all wish to have in future a lot of optical wireless connections and links, and perhaps, as you know, at the time when they discussed this Iridium telephone net and later all the network around the world, I think it is now 20 years or something that they had these ideas, it was always visible that also optics should play a big role, yes, and we hope, and I'm sure in future optic will play a big role, yes. The only point is, of course, the people with their copper cables and with RF, they will find always new last chances of technologies, yes, to use the old copper cable so long as possible. Yes, before you go to a fiber, use old copper cable so long as possible. Yes, but I'm sure it is not possible in future to hold fiber optic or photonic up from real high bit rate or high data rate communication networks. Scenario. At the end, it's also in the literature, you can also see the books available. By the way, if you like, you have, Jan, you have now on the computer my presentations.
It will be
on your computer, but you can distribute, if you like, to your colleagues here the PDF if they like.
And this project have its website.
Okay.
And
okay.
on this website, your presentation.
Okay, the PDF. That
yes.
is good. Yes, yes, that is good. So thanks. That was the second part, and let's have 10 minutes again.